The term microwave is used to describe a technique which is applicable to radio waves that have very high frequencies and very short wavelengths. At the highest frequencies, these waves can be as short as a few millimeters. Contrast these signals with the medium frequency signals used for AM broadcast, or even the very high frequency signals used in FM broadcast, and you should see why they are referred to as microwaves. In the electromagnetic spectrum, microwaves fall between the highest radio frequencies and the frequencies of heat and light. As you can see, microwaves cover a very broad range of frequencies which fall into three frequency bands: ultra-high frequency, or UHF, super-high frequency, or SHF, and extremely high frequency, or EHF. It is generally agreed that microwave frequencies typically begin at about 1 gigahertz, that is 1,000 megahertz, in the UHF band. The definition microwaves depends on circuit size in relation to signal wavelength, however, so 1,000 megahertz is not an exact figure. At the high end of the spectrum, there is important microwave work being done at frequencies as high as 100 gigahertz and above, in what is known as the millimeter waves region of the EHF band. Microwave signals, with their high frequencies and short wavelengths, have special properties which make them especially useful to us. First, there is an enormous amount of frequency range available to be exploited in the microwave portion of the electromagnetic spectrum. Secondly, microwave signals can occupy a greater proportional bandwidth and can therefore be transmitted and received with far greater information carrying capacity than lower frequency signals. Thirdly, the short wavelengths of microwave signals allow them to be focused with antennas into intense narrow beams of energy for precise point-to-point transmission. And finally, microwaves are the only radio waves which are able to pass through the Earth's atmosphere without appreciable loss, making them the only signals suitable for use in space and satellite communications. To get a better appreciation of the importance of microwave signals, let's explore each of these advantages in a little more detail. If we compare microwaves with radio frequencies below 1 gigahertz, we can appreciate the large frequency range in the microwave portion of the spectrum and the greater amount of space it provides for many potential communication services. If we consider all of the AM, shortwave, FM, and television broadcast channels, all of the vehicular, maritime, and aircraft radio communications channels, and all of the radio navigation and beacon channels below 1 gigahertz, they would all occupy just the first portion of the microwave frequency range from 1 to 2 gigahertz. The entire microwave spectrum, from 1 gigahertz to 100 gigahertz, thus has the potential to carry 100 times that 1 gigahertz bandwidth. Historically, the use of the radio spectrum developed beginning with the low frequencies and advanced to fill higher and higher bands of the spectrum. While the use of the lower frequencies is at full capacity, the more recently developed microwave region thus has considerable room for expansion and development. The amount of information a radio frequency signal can carry is directly proportional to its bandwidth. For example, if a radio telephone is to carry voice information with audio frequencies ranging up to 3 kilohertz, its bandwidth must be 6 kilohertz or more. AM broadcast radio requires about 10 kilohertz of bandwidth for the information transmitted by each of its stations, while an FM stereo broadcast containing more signal information requires a bandwidth of about 200 kilohertz. Broadcast television, being much more complex than radio, requires about 6 megahertz of bandwidth per station. A single broadcast TV channel thus occupies as much bandwidth as would be required by 600 AM stations. As we will see later in this program, the bandwidth capabilities of microwave signals are substantial, far exceeding those of lower frequency signals. Intelsat 5's microwave satellite transponders support bandwidths of about 77 megahertz, the equivalent of nearly 13 television channels, or 7,700 AM radio stations. With the growing need for high-capacity communications channels, these microwave frequencies provide the means to accommodate considerable expansion. Microwave signals have very short wavelengths, allowing their energy to be focused using special antennas. This feature allows many microwave stations to occupy an area without interference with other radio services. It provides for secure and portable point-to-point communications without the necessity of cables. Another advantage of this characteristic is that when transmitted, these microwave beams can act like searchlights to illuminate distant objects and receive their reflected energy. This is the application we call radar. Yet another benefit derived from the narrow focus of microwave signals is an increased concentration of energy within the antenna beam pattern. For example, a 1-watt microwave signal feeding a typical dish antenna yields an intensity greater than 1,000 times more powerful than one obtained from an omnidirectional antenna, one that does not sharply focus the signal. Perhaps the most important advantage of microwave signals is their ability to pass directly through the Earth's atmosphere without appreciable loss. It is this single factor which is responsible for the satellite tracking and communications that have so greatly contributed to our technological progress in recent decades. In the past, messages were sent around the world using radio waves in the medium and high frequency bands, which depend on the atmospheric layers surrounding the Earth to bounce the signals. These unreliable techniques resulted in fading and limited effectiveness of worldwide communications. Now, with modern techniques, microwave signals are beamed directly to satellites, which can receive, amplify, and reliably retransmit them to any point on the globe. Now you should have a general idea of what a microwave signal is and what it is used for. In the remainder of this program, we will explore the characteristics of microwave signals and see both how they are similar to other radio frequency signals and how they differ from them.